Now we want to look at some results and some questions that come about in rectangular hyperbola. So the first one here is looking at the area bounded by a tangent and the asymptotes is a constant. So what do we mean? So we've got a tangent and our asymptotes are the axes here. So when we have our point going through, our tangent going through x1, y1, we get this equation. So x1, y1 plus y1, x1 is equal to 2c squared. So at the x-axis, it's going to go through the point 2c squared on y1, because when x is equal to 0. And when x is equal to 0, we sub that in, we get yx1 equals 2c squared. So y is equal to 2c squared on 1. So there's our 2 points. And because we form a right-angled triangle there between the tangent and the axes, we just have to apply the area formula. So half times the 2c squared on x1, 2c squared on y1. And we get this situation, the 2 will cancel, we get 2c4 on x1, y1. Now remember that this is in the equation of our hyperbola is xy is equal to c squared. So an x1, y1 sits on that hyperbola. So x1 and y1 satisfies that. So x1 and y1 will actually equal c squared, which will cancel with the c4, leaving us 2c squared, which will be a constant. C is a constant, so it doesn't change. X and y changes, but it has no effect. That doesn't matter what it would be, that area will always be 2c squared. So there's a nice little proof. The next one is to show the length of the intercept cut off a tangent by the asymptotes equals twice the distance of a point of contact from the intersection of the asymptotes. So what does that mean? There's our tangent. And we'll use parametric form to prove this one because it's a little bit easier to manipulate. So there's our tangent there, and it's cutting off our points at the axes, which are the asymptotes. And then the point distance from that point on the hyperbola to the intersection of the asymptotes, which will be the origin. So that makes life easier. We want to prove that the distance of the tangent where it's cut off, is twice that distance there. So, well, if we're going to do that, we get our distances. So the distance 1 there, between 0 and cp on c on p. So we substitute in the distance formula, we manipulate it, we get c outside of p, square root of p squared plus 1 on p squared. Can't really simplify that down, so we'll leave it there at the moment. For distance 2, we've got our 2 points, 0 and 2c on p, and 2cp 0, which we'll substitute into the distance formula. We get a 4c squared p squared and 4c squared on p squared, which we're able to factorise a 4c squared out of that. And the square root of 4c squared is 2c. So when we start to compare it, d1 was c outside the square root of p squared plus 1. And d2 is 2 lots of c times the square root of p squared plus 1 on p squared. So there we can see that d2 is 2 lots of what we have for d1. So there is our proof. So much easier working with the parametric forms in that case. So let's have a look at some questions. So the first one here, we've got a hyperbola 2xy is equal to a squared. So prove that for all values of t, that point lies on h. So, well, that's just a case of taking those points. We're just proving that that point lies on a hyperbola. Substitute the points in. Our left-hand side equals our right-hand side, so it must be true. So then we want to find the tangent there. So find that the tangent has that equation. So differentiate implicitly and get our gradient function as minus y on x. And then substitute our points in. So the y is at and x is at on 2, which gives us minus 2 on a t squared. So there's our gradient. Substitute it in with the point at and at on 2, the x value and the y value. And then we are able to multiply through by t squared. And then we're able to collect the terms to get to what we want. So there's our nice manipulation to get our tangent. So the next part, B, here wants a point S, which is AA, and it's perpendicular. The perpendicular from S to the tangent meets it at T. So there's T and there's S. And it's perpendicular there. Prove that ST has that equation. So, well, if it's perpendicular to the tangent T, then it'll have T squared on 2 as our gradient. Because 2 on T minus 2 on T squared was the gradient of the tangent. So we've got our point, we've got our gradient, so we substitute that in, point gradient form of a line, and we were able to get our equation of our line there that we needed. And then it says, prove that as P moves on the hyperbola, the locus of T is a circle centered at the origin. So what we want is that point T really to manipulate. And we want to prove that it's going to be a circle. Now that's not as easy as it seems, because we really want to try and get T by itself here and then manipulate it and get it into X or Y and then put it into that one is going to be really hard. So that there's a little bit of a trick here. If we take our two lines where T intersects, so T's intersecting it where those two lines meet. Now the trick here, square both of these sides. Now, split these equations. So if we do that, we get the 4x squared, because this whole thing has to be squared. And this whole thing has to be squared. So you're squaring both sides there. So it's not just squaring each term. So when we manipulate that out, we expand that, we get the 4x squared, 4t squared xy, plus t to the power of 4y squared, and 4a squared t squared. Expanding that one, we get the expression there, and there's the right-hand side gets manipulated there. So when we add the two of them together, these ones will cancel, but what you start to see is you've got something in x squared and y squared, and we would want to prove that it's a circle. So that makes life a little bit easier because we're getting something in terms of x squared and y squared. Hopefully we can manipulate so t's gone, because that t should be gone. So we get 4 plus t to the power of 4, and 4 plus t to the power of 4, which is nice. Now the 4a squared t squared will cancel as well when you add those together. So you get a squared t to the power of 4 plus 4a squared, which we can factorise the a squared out of that, and leaves us t squared to the power of 4 plus 4. Now they all cancel, leaves us a squared plus y squared is equal to x squared plus y squared is equal to a squared. So it's a circle, centre of 0, 0, radius a. So there we go. That's a little bit of a trick in that one, that you have to realise that we have to square both sides to get that manipulation happening to get rid of t in that case. You might be able to get t by itself and then substitute in. Probably a lot more work. So take note of that one. Little bit different ways of trying to solve that. Looking at 2. So you got a tangent to rectangular hyperbola on that point has that equation. So we want to show that. So like we've done before, we derive implicitly, get our gradient by subbing in our two y and x value, because we've got a gradient function of minus y and x. Gives us the minus 1 on t squared. So, which we've forgotten to put in, the minus there, so we'll put it in. Multiply through by t squared, expand our bracket, collect our terms, and we have our equation as required. The next part wants us to show that the tangent cut off the x-axis at the point Q, and so it does, and then to show the line Q has perpendicular tangent has that equation. So at Q we get y is equal to 0, obviously, so the point it goes through is 4t0, and our equation of that line will require us to get the perpendicular gradient, so t squared, and then we can put that in and expand our right hand side out to give us our equation as we require. Now we've got that equation of the point through Q that's perpendicular, and we're told that it cuts at R and S, so on the hyperbola, so it must cut the hyperbola twice, and we want to show that the midpoint of RS has those coordinates. Now that is going to be a little bit tricky, because we've got to solve these two simultaneously, the equation of the hyperbola and the equation of the line through Q. So if we do that, we've got y is equal to 4 on x, so we substitute it in, and we get a quadratic. So it's not going to factorise nicely. So we go to the quadratic formula, which isn't pretty. So we substitute in, collect our terms down, like simplify where possible. We take a 4t squared out of here and take the square root of it, and that starts to make a little bit nicer. The 4t cubed and 4t, well, that's going to cancel a little bit with the 2t squared. And gives us these two values, 2t plus 2 on t, square root of t squared on plus 1. And we've got the same thing, except it's minus there. Now, getting the y values, well, it's not too bad, because what we've got to do is put it 4 over that, because it satisfies the hyperbola. So, the midpoint there. Now we've got our points for R and S. Now we want to find the midpoint of the 2 points. Should come down to that. Looks easier said than done. So we get our 2 points. So the 2 x values. And the nice thing about this one, if you look at the x values, well, they'll just cancel. Those parts cancel. And it gives us the 2t plus 2t gives us 4t on 2, which comes down to our 2t. So that's nice. That the x part works out nicely. The y part not so much, because we've got 2 fractions there, so we have to get a common denominator, which is the multiplication of the 2. So notice that out the difference of 2 squares, which is a little bit easier. Multiply through to get our numerators. And again, our numerators not too bad, because those parts will cancel. That's where we get the 16t from. We've multiplied through by t and the t squared and cleaned it all up here to get that expression, which again, we get some cancellations there. We get minus 4t squared there on the 2, which we can start to divide by that fraction. We get 4t cubed on 2, which will cancel down to minus 2t cubed. Check that carefully with all the working that's been done there. But realise that we were just adding fractions, cleaning it up where possible, expanding out where possible, cancelling terms to come down. So you would expect lots of terms to cancel if it's going to start off something that's really nasty and come down to something that looks pretty simple. So what's the equation of the locus is of m as t mu? So the midpoint, we've got x is 2t, so we could write t as x on 2, and the y value was minus 2t cubed, so substitute the x on 2 in, gives us a cubic curve there with 4y plus, so x cubed plus 4y equals 0. So that's what the locus of m will look like as t moves on the hyperbola. So there's a few questions. You're seeing how we can start to use different techniques to manipulate it. So as we've talked all the way through, your use of algebra needs to keep getting better and better as we go through. And you're seeing different techniques, so not beyond you. But keep in mind if you have to manipulate some functions that we saw here.